Alright, so today we want to look at a very easy topic or a section of the Unit 1 syllabus that speaks on scalar and vector quantities. Right? In in fifth form, students would have been introduced to these concepts, right? And it's pretty much, as a matter of fact, whenever we're talking about physics, right, it's all about dealing with measurements overall, right, and understanding how measurements work. So they had to classify them. So whenever we have a physical quantity, we, we want to be able to can distinguish between the different types of physical quantities. When you measure it, what do you get? All of that. So hence the reason why we our physicists classify different physical quantities in these two categories, right? So we have the scalar and we have the vectors. Now, whenever we talk about a scalar quantity, it's basically any quantity that whenever we take the measurement, we are able to get only the size, as you can see here, and another word for size, we refer to that as magnitude, but no direction. All right. In addition to when we talk about vector quantities, as you would have known already, it is basically any quantity that whenever you take that measurement, you be able to get a magnitude, right? Or size and direction. Now, as when you talk about magnitude, guys, we're talking about a number, right? So that number could be, take for example, 30 newtons. Now, whenever you, so for example, you're dealing with the vector force, right? Now, force is going to have a direction associated with it. Whether you're going to pull, take for example, it's a pulling force. Imagine I have a, a goat here. I don't know how to draw a goat. Right, this is a goat. Goat ears and legs and all of that. And there's a rope attached to the goat. Alright? Now, whenever I pull this goat, I'll be pulling in a particular direction. Hence why whenever, so the force or the magnitude of force that I'm going to pull with is going to be like 30 newtons, right? So, but it also has a direction. We can get an associated direction to it. So we can refer to our direction as what we call either going to the left. In this case, we'll be going to the left. Good. We can say we can classify direction as being negative in this case. So we could use a negative sign, or we just write to a negative. Good. We could say that the person is moving backwards. That's another way. That's another way of talking about directions. Good. So there are different ways or we can refer to direction. We can also use the cardinal points. This would be west. So he's pulling with a force of 30 newtons westwards or west. So there are different ways that we can talk about directions. Now here's a table that would help us to understand which different quantities would be scalar quantities, vector quantities, and so forth. And we know that whenever we take the mass of something, right, and generally we use a triple beam balance to measure the mass of something. Whenever we take that mass, we don't get a direction. We only get a magnitude. When we do weight, when we do use a spring balance to find the weight of something, we're actually measuring the force, right? So weight is a force acting down on something, right? And in this case, force is measured in newtons. Good. So we know that this is going to be a scalar quantity because take for example, you have the spring balance here now, and the object is attached to it. that weight, the weight of this object, is going to pull the spring balance down. So that's how we would get the direction associated with this. Velocity, we get a direction associated with that, mainly because of how we defined velocity. Velocity is really defined as a change in position over time. That change in position would be your displacement. Another quantity that we could write here as we speak about vector quantities, we could say displacement, because displacement is a vector quantity. We could put that there. Now there are many others, like momentum. Momentum would be one as well. So there are many more quantities that can fill in this table. What you just have to understand is that if for example we look at momentum, momentum is equal to mass times velocity. Now velocity in this case is a vector. So this in itself makes momentum a vector quantity. All right? So we can look at the root ones that are here, and that can help us to determine whether one is going to be a vector or scalar. Now if you look back at force, force is made up of, based on Newton's second law, mass times acceleration. Acceleration here is going to be the vector. All right. Now, as we speak about vector, based on our objectives here, we want to uh, resolve vectors, both the graphical method and by using calculation. We want to do addition and subtraction of vectors, using components. All right. One thing we need to understand is that whenever we're dealing with vectors, we generally use a line segment to represent the vectors. Good. So you would use a rule, of course, to get a straight line and draw a line segment. A line segment is the one that has the arrowhead and nothing at the tail. All right. Well, this is actually the tail, I must say. So let me just speak a little bit more of this. So this part, we're going to call it the head of the arrow, and this part is going to be the tail. Good. There's another way how they refer to it as. I don't remember, it slipped me right now. But what I want to also mention is the fact that what I want to mention of is the length of the vector. The length of the vector, give me a second. The length of the vector, or the length of the arrow rather, is used to represent the magnitude. And when this comes back up, we'll definitely look at how we can do this a little bit better, right? So the length here, so if I was supposed to measure a particular vector, right, I would use my ruler to measure some centimeter, right? Now when you measure that centimeter, you need to scale the diagram. So we attach what we call a scale to it. So we would say that 1 unit represents 5 meters per second, right? So for every 1 centimeter that you increment by, then it would be 5 meters per second. All right. So because we know that we cannot draw if our vector here is 30 newtons, there's no way we can draw 30 newtons in our book. So we have to use what we call a scale diagram. All right. So the scale diagram would make life easier for us. And as we said, we'll use the ruler to help us. So whatsoever length I measured on the ruler, so this length here, if I say this is 1 centimeter, 2 centimeter, 3 centimeters, yeah, right? If I know this is 3 centimeters, good. then and my 1 unit, which is 1 centimeter, represents 5 meters per second, then I'll just simply need to just multiply the 3 by the 5 in order to get the exact length, or the exact magnitude rather, the exact magnitude of this particular vector, which is going to be 15 meters per second. And this vector is going in the eastward direction. Now, similarly, when you look at this one that is moving vertically, this one, the direction is south, and based on our scale here, it's basically it's going to be 10 meters per second, right? So those are ways how we can draw or represent vectors. Or that's a recommended way that we use. So if you get a particular graph, just give me a second. If you get a particular graph, okay. So this is a recommended way that we use to represent vectors. So whenever you're drawing vectors on a graph, you would use those small boxes to guide you, and you definitely need a scale. So you'd have to think about it. Whatever vector you're drawing should be a scaled, meaning that it shouldn't be a big thing, right? It should be scaled down to represent it in a much better way. Just like with a map. A map is just a scale diagram of the actual thing. All right. Now, when it comes on to vectors, we can add, we can subtract, we can do quite a number of things with vectors, but for this lesson, we want to focus on how we would add a few vectors. Whereas when we look at a scalar quantity or scalar quantities, we would realize that it is much easier for those quantities to be added. It's quite easy. So take for example, once those quantities are of the same unit, I must say, right? So if I have 10 mangoes, right? And I went ahead and picked about 5 more mangoes. Good. Clearly, we can simply add these two sets of mangoes, and we're going to get 15 mangoes, right? The thing about so that's quite easy for us to just go ahead and add and subtract scalar quantities. Now, when it comes on to vectors now, right? It's not as easy as we think it is. Right? We have to involve quite a number of other things, right? If the vectors are not in a particular position. Now, this one here is quite fine. This example here is quite fine, where we have uh, 20 newtons due north plus 30 newtons due north. So once the vectors are going in the same direction, right, then it's easier to add them, right? So we'll just go ahead and just realign our vectors in such a way that, one behind the other, so to speak. So when we combine those two vectors, right, it would give us our new vector, which we would call the resultant. Cool. Now let's see what this thing is saying here. It says in cases where the two vectors do not act in the same or opposite direction, the resultant is found by means of a vector triangle. So this is what the vector triangle looks like. The vector triangle looks like this, where we have the two vectors. So if one vector is going in this direction, in this slantwards direction, good, and another vector here. So this is vector 1, by the way, and vector 2. One is going directly downward, so that's fine. But what we have to understand is that to find the resultant here, it won't be that easy. So one way how we could do this is by using the scale diagram method, right? And we would measure the length of this using an actual ruler. So if we get this length to be 100 meters, well, not 100 meters, let's say 100 centimeters, even though that can be a little bit big if you're looking at a graph. So let's just not use that. All right. You know, I think we can use it. No, let's not use that. Let's say it is 20 centimeters. Now, initially, you would have devised a scale to say that 1 unit is equal to, for argument's sake, let me just use a whole number, like to say 4 newtons. So this is my scale. All right. So if this is my scale, then it means that if when I measured this to be 4 centimeters, in actuality, my resultant vector, right, is going to be 20 multiplied by the 4, because 4 represents one unit, and we're dealing with centimeters, so that's going to be 80 newtons. All right, so that's how we would calculate it from this standpoint. Now, be mindful that you would have to ensure that you, whenever you're drawing these other vectors here, that they are of a scale diagram. So if this is 5, if the quantity of this vector is 5, or if the magnitude, I must say, is 5 newtons, then whatsoever length you draw using your ruler, it must reflect this. It must reflect that it's actually measuring 5. So this, because this probably wouldn't be an appropriate scale that we're using, or maybe, you know, would have to make some changes. All right, because when you realize 1 unit, so this would be about a unit and something in terms of the length. This one right here, vector 2, if I'm saying it is, if I'm saying that this is 5 newtons, good, this would just be 1 unit and a little bit. All right, so this might not be the best thing to use, right, in terms of the scale or whatsoever. I just picked some random numbers, but I'm just trying to show you, because it does not necessarily represent it properly. Then, you know, it's going to be a little bit small. But I want to highlight something important, that whenever you're adding vectors in this manner, we have to ensure that the vectors are in a position that we call the head to tail method. Head to tail method. All right, and what this tells us is that the head of one vector, right, must be aligned to the tail of another vector. So at this point, this is the tail of vector 1. Cool. So if this is the tail, this vector 2, the head must align to it, right, to achieve the head to tail method. That's what it means. There are other methods how we can do the addition of vectors, but for this purpose, we're going to just look at the head to tail method. So if, for example, let's create some space right here. Alright, so if for some reason we we had the vectors being separated, meaning that one vector is going in this direction and the other vector is like this, right? What I would simply need to do is to shift my vectors, right? I can shift the vector upward, but maintaining the direction that it was originally in. So if I shift this vector, it means that it will come on, it will be up on, it will be in this direction, right? This is where you would draw it. All right. So clearly, it is still going in the same direction as the original one. It did not shift. This is not as perfect. I should have laid it out a little bit better. Just I'm having some difficulties with the space. But the idea is that when sometimes you will get vectors that are not in this manner, right? Where they're attached to each other like this. So you now would have to make it a point of duty to shift the vectors but maintaining the direction, right? So if this is where the other one is, you just need to shift this one but maintaining the same direction, right? And also maintaining the magnitude, the size of it. In this case, this one that I drew was a little bit too long from the other one, so you'd have to maintain all of that because the size of the vector matters, right? Now there are other ways of writing or no. As a matter of fact, whenever we get vectors that are that whenever we put them together, they form a right angle, right? We would have to apply what we call, the Pythagoras theorem to find the resultant. Just bear in mind that this vector here is using what we call the tip to tail method. It's the same thing as the head to tail method, where you would ensure that the head of one vector touches the tail of another vector. All right. So most of us should know what Pythagoras theorem is, but it's simply, having a right angle triangle, right? That right angle triangle, what it tells me is that uh, that whenever I add the short side, whenever I add the squares of the short sides, I am able to get uh, the long side square. I don't know if I said it properly, but it's a very simple thing to remember, right? In terms of the formula, a squared plus b squared is equal to c squared. Just always remember that whenever you're choosing a, it must be one of the short side. Whenever you're choosing b, it must be uh the one. Let me go back over this. Now c is the longest side of the triangle, right? So if that's the longest side, then these two here, is clearly less than, in terms of the length, is less than that of C. So this is why I said when you must square both sides here, right? So we'd have a squared plus b squared plus c squared in order for us to understand this, right? So it is like this: a squared plus b squared is equal to c squared. So we can use this approach to find what would be the magnitude of the hypotenuse, or the long side, or the resultant of the vector. So in this case, it's quite easy. If I know a already from this example, a is 3, so a is 3, then b is 4. Let's just imagine that we don't know what c is. By applying Pythagoras theorem, we can get a thing like this. So a squared plus b squared is equal to c squared. Whenever I do that, I get a thing looking like this: 3 squared plus 4 squared is equal to c squared. Remember, I want c, not c squared. So it means then I would have to It means then I would have to find the square root to get rid of the, would have to find the square root of this side, but by finding the square root of this side, I would have to square root the other side. The square root of 3, let me just write 9 instead of writing that again. 9 plus, we know that 4 squared is 16 is equal to c. Well, let me just rewrite this. So the opposite of a square root is square. So if I have both of them on the same side, it's going to cancel out. So that's how we would get rid of the square. So c is equal to, when we sum up this here, we get 25. So the square root of 25 is going to give us a value of 5. That's how we get 5 as the magnitude of this vector here. Alright? Now, remember now when you're dealing with vectors, there is a direction associated with it as well. Right? And if we go back on this example, now we want to find what direction our resultant is from the starting point to the ending point, right? So your resultant is really that displacement from the starting to the ending point, right? So we want to find that angle that is between those two vectors. In order for us to do that, because we are dealing with a right angle triangle, we can apply what we call some trig ratios that we're going to look at in depth a little bit so that you will understand. Now, this is my right angle triangle, right? Now, the right angle triangle, we have the sides have some specific names. We know that the longest side is the hypotenuse, right? Longest side. It's called the hypotenuse. Now, the side that is beside the angle, right? Excluding the hypotenuse, because we know that the hypotenuse is beside the angle that we're focusing on. But what I want to say is that any side that is adjacent to, right, the angle that we're focusing on, right, is going to be the adjacent. Any side that is beside it, other than the hypotenuse, is going to be the adjacent. Now, when you look at this angle is opposite to this side. Hence why they refer to it as the opposite, because just like, you know, a mirror, so to speak, this is a mirror and you're here, right? The opposite end would be over on this side, right? So that's the reason why we can say that this part is going to be the opposite. It's opposite from the angle. So you really use the angles to kind of create a picture as to how you come by these things, right? Now, with that being said, there are some trig ratios, and you probably would have known them already, right? Here's an acronym that we would use. The acronym is SOHCAHTOA, where, you know, we have broken it down for you, where O stands for the opposite upon the J, and then H means hypotenuse, I must say. So sine of the angle is equal to opposite over the hypotenuse. Whereas now cosine of an angle is equal to the adjacent over the hypotenuse. Tan of the angle, or the tangent of the angle, is equal to the opposite over the adjacent. Now, let's see if we can look back at this example. When we look here, we realize that our angle is at this point. Good. We know that this is our hypotenuse. So if this is the angle, then this side A is going to be the adjacent. Use ADJ to represent adjacent. Then this side is opposite from the angle, so we call that the opposite, OPP. We know those values already because those were given to us as the magnitude. So because of that reason, we're going to just simply use the tan ratio. So we'd say tan theta is equal to opposite over the adjacent. Opposite in this case is 4, adjacent is 3. In order for us to get the angle by itself, we have to tan inverse it. So by tan inversing this side, that's gonna yeah. So in order to get rid of the tan on this side, we have to, bring it over here, and the opposite of tan is tan inverse. So we're left with theta tan inverse of 4 upon 3, and that would give us a value of 1.33, but we still need to tan inverse it. So when we do this now, do a thing with our calculator, press the shift button and press the tan, if you're using a Casio, shift and tan will give you tan inverse, and you multiply that by the 1.33, and sometimes it's recommended that you have more than 2 decimal places, right, because of how sensitive the tan ratios are, and yeah. So at this point, the angle that I'm getting is 53.12 degrees. Now we could use another trig ratio. We could say opposite over the hypotenuse. So we'd use sine of the angle, just to clarify and to check if it makes sense. We know the opposite as 4 already. We found the hypotenuse to be 5. So I'll stick up in here. So sometimes you will have to find your hypotenuse first before you go ahead can find your angle, or stuff like that, depending on which side is given to you. So if you did not know the adjacent, but well, you would have to know two of the three, right? Because you need some information to find some, right? Or they could even give you the angle. So it's a whole lot of stuff. But let's look at it now. So 4 divided by 5 is 0.8. So theta is going to be equal to sine inverse of 0.8. So let me find sine inverse. Shift sine gives you sine inverse times the angle gives us the same 53.1. Well, in this case, it gives us 53.13 degrees, and as we said, it depends on how much decimal points you round this off to, right? That is what would make that a little bit different, but it's the same answer. So we have the concept right. All right, so that's how we would approach a thing like this whenever the two vectors are at right angle to each other. So if one is going north and the other one is going east, then they can form, what we would say now, they can form a triangle, or they can form a right angle when they join each other. So in order for me to join these two, I can do one of two things. I can either shift this one to the right, or I can shift this vector to the left. So what I could do is, let me show you, or I could say it will end up being the same thing. So I'm going to let this one is A, this one is B. I'm going to shift A, so I'm going to rewrite B here. But all I'm doing is taking this one, moving it all the way to this side. So I shouldn't use that arrow, okay? It might confuse you, right? All I'm doing is just pushing that vector to this side so that the head of this one touches the tail of this one, of the vector A. Alright, now we can also look differently at vectors, right? So when we look at two vectors that are at right angle, right? Those vectors are let's look at it. Yes, so when we have two vectors that are at right angle, those two vectors is going to produce a resultant, a single vector. Now that single vector, has an effect of the two other vectors combined. So with that being said, if I have just a single vector that is tossed randomly across the screen, so just like this one is randomly tossed on the screen like that. That vector is now going to have two components associated with it. So this runs us to, I think, what we call resolving vectors. So the way how we're going to resolve this vector is that our way how we can say way how we can talk about this vector is to say that it has what we call a horizontal component and a vertical component. All right. So we would expect that our vertical is going to be like this. So that's a vertical component. Then then the horizontal would be like this. Now mind you that we would expect that our angle would be here because of the nature of this vector. So if this vector was like from the ground level, so let's imagine that it's on the ground, right? We would expect that this is going to be the angle that that vector is raised from the ground, so to speak. All right. So now we want to do a little mathematics in a sense here, right? What is it that we're going to do now is to basically form out a right angle triangle, right? And by forming out the right angle triangle, I need to extend this a little bit so that it makes it's more uniform. All right, I could do this. I could erase a piece of this. All right. So I have resolved my vectors, but now I need to know what does the horizontal component is. What is the horizontal component? And in order for me to do that, I will know, form what we call a right angle triangle, or we could refer to this as forming a parallelogram, so to speak, right, between the components. So by forming a parallelogram, we realize that we have two right angles coming out here, right? Two right angles. Now, guys, on this side of this triangle is going to be the same thing in terms of the vector that is in green on this side. It's going to be the same. So I could simply say if I found this side to be the opposite, right? Then it means that whatever value I got for this side is going to be the value here for your vertical component. Okay? Now let us apply the trig a little bit here. So we know that this is our hypotenuse. All right? And we know that this is going to be our opposite. And we know that this side is going to be our adjacent. All right? We just want to find the relation between this vector and what is it that we're going to name this side? What is it we're going to name this side? What value does it have? That's what we're trying to do here. Now, when you look at the formula that links the opposite in terms of the formula here for the opposite, let's look at that formula. That formula would be sine theta is equal to opposite over the hypotenuse. Because this side is the opposite, we just want to, what would I say? We just want to find out the value, so to speak. Now, your hypotenuse would be a resultant. Your resultant would already have a value. So if our resultant, I would just call this vector, we'll just call this v based on this example here. That vector is v. Now, let's look at this. Let's just make the opposite become the subject. So with that, we're going to have the hypotenuse. So sine theta times the hypotenuse, in this case, which is v, is equal to the opposite. So with that being said, the opposite, or this vector, the vertical vector, is going to be v, which is the value of the actual vector here that we're looking at, times sine theta. All right, then we want to know what is the adjacent, so to speak. The equation that links that is this one, that it says cosine is equal to adjacent upon the hypotenuse. All right, so with this equation, we can make the adjacent become the subject. So we know that the adjacent really is equal to the hypotenuse times cosine, and we know that hypotenuse already is v, so v times cosine theta would give me that value for the adjacent. Now let's just look at an example. So an example here. So let's got one of the example, and the other one is for you to do for homework. So the question says an aircraft is traveling 35 degrees east of north at a speed of 310 meters per second. Not meters, but I'm mixing up. Not kilometers per hour, rather. So it says calculate the speed of the aircraft in which it's moving in another direction and the easterly direction. Now with that, we have to convert our kilometers, or our speed into actually a vector, right? Or we should calculate the speed into velocity, so to speak. So how we're going to do that is we know the speed is equal to 310 kilometers per hour. All we're going to do now is to do a little bit of conversion, because we just want this in meters per second, right? So that we can actually appreciate it some more. So 310 times, so now kilo is basically a thousand, so that's 1,000 meters. So 310 times 1,000 meters divided by, we know that in 1 hour, that is it's actually 3,600 seconds that would take to make up 1 actual hour. So with that being said, we can now simply deduce what the velocity is, or the speed rather. Speed velocity